Hello and welcome to our talk. I'm Fabian Stöter from Inria in France.
And also hello from my side. I'm Stefan Uhlich from Sony Corporate Research in Germany.
Yeah, so welcome to our talk on current trends in audio source separation. The aim of this talk is to give a quick overview on source separation methods, and we try to talk to make the talk agnostic to speech and music, even though that we know that the methods that will be used are particularly different for each of these particular tasks. But we hope to find a way to get you excited about current trends, because there's a lot of things going on right now in source separation. So the talk will be outlined as followed. First, we briefly introduce some basics on audio source separation, and second, we want to name a few recent topics in separation that are hopefully of interest for even people outside of the community. And last but not least, the current achievements were undoubtedly accelerated by open source tools and datasets, so we think this is a good way to also emphasize and introduce a few of them. So let us start with the introduction to audio source separation. Stefan.
Yes. Audio source separation refers to the task of separating a mixture. Here it's music, so we have a song, into its constituent sources, here instruments. So for example, this song consists of a guitar, vocals and a piano, and what we want to have at the end is really the individual tracks for each of the instruments. Problem is known to be ill-posed, so it's an inverse problem, because we often deal with an underdetermined source separation problem. So very briefly what this means is that, for example, for monaural speech enhancement, we only have a single time sample x of n for two sources, for speech and noise. Or for stereo music separation, we have a single sample xn for 4 stereo sources, for bass, drums, vocals and all the remaining instruments. And the classical methods that we knew until 2012 basically worked only to some extent.
Yes, so the first methods that used deep learning were already introduced in 2013. Neural networks were mostly designed as a denoising autoencoder, and these systems are useful, for example, if you want to separate male vocals from female vocals. Traditionally, most systems were performing in the frequency domain, and now many systems are performing separation in the time domain to avoid drawbacks that we see in time-frequency masking, such as that phase information is not fully utilized. The main point here is that the models that are used today can be used in different settings, so they are interchangeable depending on the loss function. For example, a deep learning model can be used in a setting where we want to separate different source types, for example, vocals accompaniment, where the loss function is adjusted to compute a loss for each individual output. And the latter is a system which is permutation invariant training, or PIT loss, where we perform separation on same sources. In this setting, we assign different loss functions to each of the output, but also compute all different permutations of these individual outputs. Okay, so let's look at the performance over time, which means we look at a specific task here, which is the speech separation task, and the plot shows the scale invariant signal to distortion ratio improvement, or SI-SDR, and on the x-axis we see the year of the method being published. So what we can observe is that we see basically a flat area from 2015 to 2018, and that was a time when people tried to find out what is the best way to actually phrase the problem of the permutation invariance for speech. Deep clustering was the first that actually works. And we see another milestone, which is the Conv-TasNet here, which is a performance improvement of almost 5 dB SDR in 2018. We see here that this is a big improvement, and we will later introduce or show what are the different achievements in this work. So we identify 2 milestones. The first one is deep learning approach for speech separation that includes solving the permutation problem. The first idea here was deep clustering that came out, and the assumption in deep clustering is that, and this is a time frequency approach, that for each time frequency entry we assume that one source is dominant. The network is then trained to produce an embedding vector, so that a clustering step which comes after would then cluster the embedding space into binary masks. Permutation variant training, the second approach, gets rid of the clustering step. That means for a pair of speakers, compute a loss for all possible assignments here. The assignments with a lower, let's say, mean square error is then chosen, and the network is trained to minimize the corresponding loss value. The second milestone is Conv-TasNet was the first network that introduced and surpassed results of time frequency method. It is important to understand that Conv-TasNet did not have one single contribution that made this performance. But before we explain the network in detail, maybe it would be interesting to listen to the gap between these two milestones. Let's first hear the mixture.
Numerous works of art are based on the story of the sacrifice of Isaac.
nature of knowledge.
And now separation with deep clustering.
Numerous works of art are based on the story of the sacrifice of Isaac.
Philosophers of education often differ in their views on the nature of knowledge.
And compare that with Conv-TasNet.
Numerous works of art are based on the story of the sacrifice of Isaac.
Philosophers of education often differ in their views on the nature of knowledge.
I think that's a major improvement. Okay, so let's go into a general source separation architecture like the Conv-TasNet, but the principle holds to many other networks as well. So almost all of them now consist of an encoder, which encodes a segment of the mixture waveform to some kind of time frequency-like representation. Then, of course, we have a separator. The separator, we're performing a time-distributed operation on the encoded input. The output of this can either be a masking operation, like shown here, or it can also directly output separated, encoded, still encoded representation. And what we then still need is a decoder to reconstruct into a waveform, like an inverse short-term Fourier transform, but this can also be trainable. And last but not least, we need a loss function, compute the error between estimated separations and the ground truth. So let's try to dive in deeper into the Conv-TasNet. It consists of a number of tricks, as I mentioned, and that each contributed to the great performance of almost 5 dB difference to the previous state-of-the-art network. Regardless of the actual detail of the network, the one that contributed most to the performance is actually the encoder and decoder part, because here many tricks were introduced. So the encoder and decoder is a fully trainable transform, and as I show here in this paper, the effect of significantly reducing the window size or the kernel size of the convolutional networks greatly benefited to the performance. That is almost 2 dB in performance. All the other tricks, for example, the time domain loss, the normalization, which is a layer norm, and the separator itself contributed as well, but none of them had such a large improvement.
So this brings us now to the second part of this presentation, and in the second part we want to talk about 5 current trends in audio source separation, as well as we want to identify some open problems. So the first trend that we can see is the transition from supervised separation to universal separation. In supervised separation, we have quite some prior knowledge about the separation problem that we want to solve. So for example, we know a priori the number of sources that are there in the mix, and typically also the number of sources is quite small, so either 2 or 4. And even more, we know also what type of sources we want to separate. On the other end of the scale, we have really universal separation, where we have an unknown number of sources, and even more important, also we deal with an unknown source type in the mixture. So we really don't know a priori what type of sources are there. This universal sound separation problem is not yet solved, but we can see recently a lot of progress that people have made towards this goal of universal sound separation. And one thing that is now possible is to do source separation for an unknown number of sources. And there are 2 references that you can see here. So for example, in this approach here, the idea is to recursively split out one source from the mixture using a one-and-rest speech separation system. The network has 2 outputs, S of t and R of t, where S of t contains the estimate of one sound source, in this case here of one speaker, and R of t contains the remaining speakers that are left. And the idea is now to iteratively apply this one-interest speech separation system to separate the mixture until basically we have really split the mixture into all these speakers, into all these sources. So for example, here for 3 speakers, we have to apply twice this network until we really have all the 3 speakers separated. And the recursion is stopped whenever the residual output doesn't contain speech anymore, which can be, for example, checked with a simple voice activity detector. Another progress that has been made towards this direction of universal sound separation, you can see on this slide here, is source separation for a large number of classes. So for example, the system 1 that you can, so all the references you can always find at the bottom of the slide. The system 1 is capable of dealing with 527 audio set classes, and it's doing this by using a conditioned network f of x and c. So f denotes a network and it gets a mixture x, and using a one-hot encoding of the class that we want to separate, basically we can separate out one sound source from the mixture. And the training for this system on the audio set dataset is done in a 2-steps approach. So first, a sound event detector is trained, and this sound event detector is then used to identify anchor segments which can be used for training. And using this approach, basically we can train a system on 527 audio set classes, which is really amazing. Another progress that has recently been made is to train separation systems on datasets where we only have mixtures. And the paper by Google, as this reference 3 here, proposes a mixture invariant training, which we will see in a minute, so therefore it's only mentioned here. A second trend you can see on this slide here is being able to deal with imperfect training data. So imperfect could mean several things. Could mean that we have only weakly labeled data. And the idea of 2 references that you can see down here is basically to use sound event classifiers in the case where we have weakly labeled data. So the system that you have seen on the slide before that was trained on audio set was already such a system. This is this reference 2 here. There's another interesting work from Mitsubishi Electric where they show basically how to train a separator when we have only maybe frame level information, frame level labels, or maybe only clip level labels available. Imperfect could also mean that we only have access to unknown mixtures of sources in the training data. And Google recently showed with their mixing invariant training that it's still possible to train a separation network on such data. And basically what they do is they extend permutation invariant training to their mixture invariant training. And you can see basically this transition here. For permutation invariant training, we have access to the individual sound sources, which we mix together. And then we have our separation model that demixes this mixture and creates estimated sources. And then we solve this permutation problem in order to obtain the minimum loss. And by this, then we can basically backpropagate and update the separation model to improve the outputs, the estimated sources. This is possible in permutation invariant training because we have access to the individual sound sources. Now that we have only mixtures available, we don't have to solve a permutation problem here, but we have to really solve a mixing problem. We have to decide for every estimated source whether it goes with the first mixture or with the second mixture. And this is solved by finding a binary mixing matrix A that you can see here. And this mixture invariant training is really very interesting, and by this it's possible to train on training data which only contains mixtures of sources. Finally, imperfect could mean that we want to train speech enhancement systems on noisy speech. Speech enhancement is also a source separation problem where we want to separate noisy speech into clean speech and into noise. And in order to train such speech enhancement systems, ideally we have access to large amounts of high quality multi-language speech data. However, obtaining this data is not straightforward, and what people often use are speech datasets that were created for automatic speech recognition, for ASR. And the problem is that this data set often still contains noise, and maybe even on purpose contains noise, because we want to have our ASR system to be robust for noise, for typical noise that can be there. And one example is the Mozilla Common Voice dataset, which is very nice because it's multilingual, has many speakers, and is really also a large amount of samples. But there are typical noises like microphone switch on sounds or even sample dropping that we actually want to remove by speech enhancement. The question is now, how can we train speech enhancement systems if we don't have access to really clean speech in our training data? There's some work that tackle this problem with an approach that is known from image denoising. It's called noise-to-noise approach. And there's another approach where a kind of bootstrapping is used, where we have access at the beginning to a smaller clean speech data set, and this can be used to bootstrap then the training on the larger noisy speech training data. But this problem is still unsolved, and the mixture invariant training that we can have seen on the slide before we cannot use because the mixtures that we deal with, they are not really random, and that's an underlying assumption of the mixture invariant training. Okay, so the next trend is perceptual loss functions for speech enhancement. Perceptual measures are commonly used for speech enhancement. For example, perceptual evaluation of speech quality, PESC. There are the composite measures that measure the signal quality, background noise intrusiveness, or the overall quality. And there's also STOI, which is a good measure, or that very well correlates to speech intelligibility. And those perceptual measures have been used for speech enhancement systems as additional loss terms in order to improve their perceptual quality. They are non-differentiable, and then there are different ways how we can basically bring them into the training, either by approximating them, and by this obtaining differentiable terms that we can directly use for training, or by treating them as kind of a black box and then using, for example, finite differences, the quality net approach or matrix gun approach. And this really helps to improve the perceptual quality of the separated speech, and there's a lot of work really going in this direction. However, in contrast for music, perceptual measures are not really that commonly used. There is also an estimate of perceptual quality for audio source separation, which is called PEACE, which stands for Perceptual Evaluation of Audio Source Separation. And also quite recently by the University of Surrey, it was checked whether this PEACE scores still correlate well with human perception. And although they showed that the APS, the artifacts-related perceptual score, showed a good correlation with human perception, it's still seldomly used for music separation. There's one recent approach from MIT and Spotify, which I would like to mention, and which is very interesting, is to make speech separation, but also vocal separation, more perceptual relevant by using information from a perceptual codec like MP3. So the idea is, and the idea we can see here is that instead of using the normal loss that compares the ground truth signal S and our estimate S hat, we turn this into a perceptual loss by using a low bitrate codec, for example, low bitrate MP3. And we now compare in the loss function not S and S hat, but the low bitrate coded versions of the ground truth and of our separation. And this low bitrate MP3 codec will have removed everything which is basically not important for our perception, and therefore it should be more meaningful to compute the loss on phi of S and phi of S hat instead of the original S and S hat. In general, as we can also see from PEACE, there's really the need for more work on perceptual measures and also loss functions for music. And currently there's really not the tools, or at least they are not used by researchers for doing a perceptual evaluation. And to show you that this is important, we have prepared a demo where we will compare Conv-TasNet and OpenUnmix for a song where both have the same SDR for the vocals, but you can clearly hear that both are different in quality.
Alright, so I first playback the mixture, then the vocal separation from Conv-TasNet, a time domain model, OpenUnmix, a spectrogram model, and the reference.
We are saved by our Maker. We are saved by our Maker. We are saved by our Maker.
I think from this it's clear that the spectrogram model has more pleasant artifacts. Another trend is to combine source separation with other tasks, such as classification tasks. And this is a long-standing problem and questions we have in our audio separation and many related tasks, which is, well, given we have a perfect separation system, would we then be able to get a better classification system or a better recognition system for speech, for example? There's a recent evaluation campaign for the 2020 DCase, where for the first time they ask for the task of sound event detection to have a separate evaluation for a source separation system and a sound event detection system.
Okay, and this slide has another example where multitask training is beneficial. And this is multitask training for speech enhancement. And what has been noted in the references that you can see here is that basically when we have a system and we want to do speech enhancement, actually we are only interested in the enhanced speech, basically only in the separated speech we're interested. But it's beneficial to train at the same time also the mask for the noise component, and to have really a loss function which is containing not only the error that we do in the speech prediction, but also the error that we contain in the predicting the noise mask. And this additional task acts as a regularizer, and we can observe that the speech mask generalizes better. And here are results from a colleague at Sony, where he trained a system which only predicts the speech mask, or which predicts speech and noise masks at the same time. And we are only using the speech mask at the end really for the speech enhancement, but here for k equal 2, basically both masks are trained at the same time. So this is like a multitask training. And you can basically see here, if you compare adjacent bars, that basically, for example, just look here at the PESC. This is on voice back and demand corpus on VBD. We can always see that we can see an improvement for Conv-TasNet, and this is here for another approach in the STFT domain. We can see basically for k equal 1 doing the transition and also estimating at the same time the noise mask or the noise component, we see an improvement. So it's beneficial to train to do this multitask training for speech enhancement. Okay, so finally, last trend is source separation is now doing the transition from research to deployment. This is because of two reasons that we can see this commercial use of audio source separation. The first one is that the quality really reached a level that we couldn't think of 5 years ago, and also the computational resources that we have available on edge devices like a smartphone are sufficient for doing real-time inference. And one example is real-time speech enhancement, where as already said, speech enhancement is to separate noisy speech into speech and noise. You can find many demos on YouTube where people are trying with vacuum cleaners and all this stuff that you can think of how good the speech enhancement system works. And it's really quite fun to watch those videos. And such real-time speech enhancement has really also gained more importance now that there are much more video conferences because of COVID-19 and people having to work from home. Second example is karaoke, where source separation can be used. So traditionally, karaoke uses cover version material, which is already split into vocals and accompaniment. But this has two drawbacks. The first is that not all songs are then available for karaoke. And the second one is that there's also a varying degree of quality of those karaoke songs. Okay. So what we can do now is we can use source separation, which allows us to enjoy a karaoke version of any song by doing a separation into vocals and accompaniment. From Spotify, there's the sing-along, which allows you to turn down the volume of the vocals, and that basically you can sing yourself to the song. And another one is from Line Music, in the Line Music app, which also realizes the karaoke feature by using source separation from Sony really real-time on device. So finally, two more examples where source separation really made it into a product can be seen here. The first is an intelligent wind filter, where source separation technology was used by us for the Sony Xperia 1 Mark II. And this wind filter allows you to shoot outdoor movies without disturbing wind noise sounds. Another example is to use audio separation for upmixing of movies. Upmixing refers to increasing the channel count, for example, to go from stereo to 5.1 or from 5.1 to Dolby Atmos. And Sony Picture Entertainment released this summer a 4K Ultra HD upmix of several movie classics, and Sony AI separation was used in two movies, Lawrence of Arabia and Gandhi, to create the Dolby Atmos versions. So these were now 5 recent trends for source separation. There are some more open problems that we found. So we already mentioned some when talking about the current trends, but there are some more that we just would like to briefly mention. First one is that there's currently, in our opinion, a lack of an ecosystem for speech enhancement with a sample rate of 48 kilohertz. There's no dataset actually, or no large-scale dataset available that we can use. Voice bank demand corpus is very small, and the Mozilla ComVoice dataset is noisy and also band limited. And not only the data is missing, but also the perceptual measures like PESC are only there for 8 kilohertz per 16 kilohertz. So that's also missing when we want to go for really studio quality speech enhancement systems. Another problem that still needs to be solved is really phase reconstruction for music separation. There's a lot of work in this direction, but not really yet a breakthrough that we can see. And this is in contrast to speech enhancement and speech separation tasks, where we really can see that phase information, phase reconstruction really helps the separation system. And finally, what we can see is already work using transformers for source separation, but not they are not yet dominating source separation models. They're not yet so commonly used, despite really dominating the sequence modeling and natural language processing. And we think that more will come in this direction in the future, where people will really use more transformers for doing the sequence modeling for source separation.
And the last section of this talk is about ecosystems, dataset, and about competitions. And these are very important for the community, as I will show in the following example. I will go back to 2019, beginning of 2019, and at that point of time, one of the state-of-the-art methods for music separation was developed by Sony Corporation in 2015, or based on a method in 2015. And up till then, no one was able to get to that kind of performance, especially no open system was released yet, neither pre-trained models nor just the source code. So there was a huge gap of almost 2.5 dB between open methods that were released including source code and state-of-the-art, and that really made progress, especially for students, very, very difficult. So in 2019, that all changed, luckily. So there was many systems proposed in 2019, all open source, and also with pre-trained networks from OpenAmix, from us, and DMAX, from Facebook AI, Splitter from Deezer, and the NASA library. And all of them come with pre-trained networks, and that really helped to really kick off source separation. If you look, for example, at the Splitter repository, it's almost 11,000 stars on GitHub, so it's hugely popular, and this helps many people now to get into source separation. And we see the same trend in speech separation as well. Previously, there were many separate paper implementations that you can find, and also some of them had pre-trained models. And we see a similar trend in speech separation, where state-of-the-art models such as Conv-TasNet were hard to reproduce and mostly lack efficiency. Asteroid was released for PyTorch, which is a general source separation toolbox for speech separation that was able to recreate all of the state-of-the-art systems pre-trained on all of the data sets, so that people can start and do research. Now, there's a few more other tools that are very important for research on source separation, and many people don't think of the importance of these tools. For example, sampling strategies, how you would actually combine and assemble your data set. There's many ways. For example, there's a tool called Scaper that allows you to reproducibly create data sets based on single utterance or single stems. There is a Muta library that allows you to create augmentations or render augmentations on the fly. There's the Wave Augment from Facebook AI that does the same thing, but time domain signals very efficiently. And also, there's a continuous trend on moving more and more things to the GPU, and that is very helpful. And last but not least, very important, the I/O systems for loading audio or saving audio dramatically have improved in the last years, and that make it possible to scale source separation systems. Because when you think about it, source separation, training from raw stems that combine all these stems into mixtures on the fly in a data loader that will be subject to a huge number of I/O operations on your systems, and you need efficient data loading methods. For example, in TensorFlow I/O, we recently introduced highly efficiently load wave files that increase the loading performance by a factor of 10 compared to other loading libraries. So we mentioned already a few data sets. Briefly, we can categorize this in single utterances or single track data sets like the MetLDB or Slack or Wall Street Journal and so on, where people can then, using, for example, tools like Scaper, combine or render their own data sets. There's also a need for supervised separation datasets where there's an agreement or which kind of mixtures you want to distribute, for example, the Wall Street Journal 2 mix or the Libre mix datasets. And last but not least, there's now datasets that we already introduced, the AudioSet, White Mix, and Freesound dataset that have a huge number. AudioSet, for example, has 2 million videos that are tagged with audio that can be used to create systems that are able to separate any kind of sound. And also I want to mention upcoming competitions in the field of source separation. And the first one is the upcoming SciSec 2021. We will hopefully get news out in the end of this year.
A second competition for speech enhancement is the Deep Noise Suppression Challenge. The first challenge was together with Interspeech 2020. Which was quite successful and many teams participated, and there will be a second challenge that started now. The results will be shown on ICASP 2021. Okay, so this brings us now to the last slide, to the conclusions. So at the end, is the problem solved? And in order to say whether it's solved, we need to have a target, and the target actually should be that at the end we want to have a system that achieves human auditory analysis performance in all listening situations, which was like a goal set by Dalian Wang. And thanks to deep learning, a lot of progress has been made in the last years. But from the contest results, we know that we are still not yet there. And there are still songs, for example, where we know that the separation quality is not sufficient and where we need to improve.
Okay, thank you for your attention. And of course, if you have any questions, please contact us.